Okay, so we're now on the fourth video, which is looking at first level modeling of subject responses. So if you remember, we so far pre-processed our data, checked that the quality of it's okay, and we've looked a little bit about automating the pre-processing procedure. Now what we want to do is to take that pre-processed data, which has hopefully been corrected for various artifacts, and try and estimate at each point in the brain. So for example, in this figure here, with the crosshairs, we get this response. This is the signal across all the volumes in the time series. And we want to build a model with some explanatory variables that we think, factors that should be causing signal here. Some of them will be neuronal in origin, and some will be artifacts like motion. So the key thing is, while we have corrected for motion, there's still that aligns the images from one volume to the next. But when you move your head through a magnetic field that's being excited using gradients, there will be intensity variation in the data that's left in the data. So motion correction corrects for the head position, but it doesn't correct for the variation in signal intensity that you get from motion. So for that reason, we include motion parameters, those 6 parameters: movement in the X, Y, and Z axis, and rotation in the X, Y, and Z axis as nuisance regressors. So we're going to build a model specification, which has a number of explanatory variables. Some of those will be task related, where we think there's some stimulus or response that should be associated with neuronal activity. And some will be just artifactual, like motion or, for example, respiration, and things like that. Okay, so that's what we're basically going to do. Then we'll try and estimate the parameters. And these are just a bit like in the equation of a line. They're scaling factors, which basically says the degree to which I have to adjust the height of my predictors in my explanatory variable to best fit the data. So once we do parameter estimation, we'll have a beta image for every predictor or every column in our design matrix. And we can then test a hypothesis. So we can ask a question about whether are there any brain regions which respond at all, so versus baseline. Or we can ask whether there's more response in condition A versus condition B, for example. An important point actually regarding correction analysis in imaging, fMRI I should say, is that the bold signal isn't stable in time, it drifts, and we'll deal with this later on. But a consequence of that is that, along with other factors, the bold response isn't quantitative. Okay, unlike, for example, perfusion, where we get units of, milliliters per 100 milligrams of tissue per minute. In the case of imaging, the units are arbitrary. And that's probably not surprising. But as a consequence, we generally have to talk about response in one condition relative to another. So when I was saying versus baseline, you would be required to have a sufficient amount of resting baseline within your analysis, within your task design, to be able to do that. You can't just look at the betas of one condition in isolation of everything else. Okay. So once you've tested the hypothesis, we do that using contrast. So we compare the betas, we basically subtract them. Technically, it's referred to as a weighted sum. So we say, if we want to identify brain regions more active in condition 1, or condition A than condition B, we subtract the scaling factors, the betas for condition B away from condition A, and then we test if what's left over is significantly different from 0, in essence. Okay, and then we take that difference value and we basically test whether that magnitude of difference is significant given the residual variance in the data, the unexplained signal. And that's what we're going to do today. Okay, so this is a pipeline we talked about before. So we've taken care of this half of the pipeline here. We've prepared the data, and we now have smooth normalized images. So we're going to build a design matrix, which is a set of explanatory variables, as I've mentioned, and we're going to fit it to the data using the general linear model. This will give us parameter estimates, or beta images, which will then test our specific hypotheses using contrast to compare the betas, and then assess whether those differences are significant under the random field theory. Gaussian random field theory, which is just a method for multiple comparisons correction. Okay, so just to reiterate roughly what fMRI is doing, we have some task stimulus. Okay, so here is something control condition, then a task condition, control condition, task condition. And we would expect that the neurons are activated during our task condition. So you can see the responses are higher here, and they're low during the resting control condition. But of course, we can't measure the neurons directly. So instead what we do is we take a model of the single pole response we'd expect to see if a neural population was being activated. I mean, that's been very well established. It's called this canonical. It's called the hemodynamic response function. So you see, generally, there's initial activation. The response peaks at about 4 to 6 seconds. Then it drops down. You get this undershoot, and then it settles back within 20-25 seconds. Now this here is what's called the canonical HRF. It's a model of the hemodynamic response function. In reality, there's this what's called an initial dip as local oxygen is utilized, and then there's a flood of oxygenated blood which causes a big increase in the signal, and then it all stabilizes and come back to equilibrium. But typically, most analysis packages ignore the initial dip. So typically you see something like this. Okay, but the key thing is it reaches peak about 4 to 6 seconds after the start of the stimulus. So when we multiply these two parts together, this input function, stimulus, basically supposed to represent what's happening where the neural populations are activated, with this slow hemodynamic response, we get a predicted pattern of hemodynamic response. Okay, this is our predicted bold effect. So this is the pattern of bold we'd expect to see in any brain region where the neurons were behaving like this. So very quiet and much more active during the task, very quiet during rest and active during the task. This is what we see. So you can see that it's delayed and its shape is slightly weird because what we get is a linear summation of the response. And then you get a plateau, saturated plateau, and then it switches off. It takes time to come back down. Okay. Hope that's clear. So what we're going to do first is we're going to do a little bit of messing around with some scripts to build regressors and design matrices in the command line. Then we'll build first level models, and we'll do some contrast to explore the significance of the results. Okay, so let's switch back to, let me just check that everything's going okay with the recording. Yes, so I'm paranoid with it now. So let's go back to mobeXtra. So there's a folder here called code, which I didn't refer to previously, but what I've done is I've created some code so we can change directory, cd code, and we ls, and you'll see these codes here. Now, these ones down here, I've basically just taken from the Cambridge website. They're not, I can't take any credit for them. But what I've done here is create some other little codes. Sometimes I've stolen a little bit of code from these bits for this. But these basically hopefully just illustrate some of the principles. So we type in open code 1. We'll see this. And this is just a little bit of MATLAB code. And hopefully they mostly are fairly well commented. So here anything in with a percent sign is a comment. Okay. So if you want, you can simply just press play. But let me just go through what the steps are. What it's doing. So we initially just set a random number generator, and then we create a vector called y, which starts at 5, goes up in steps of 3 until it reaches 50. Okay. Anywhere where there's a semicolon at the end, it suppresses the output, so it's not written out to the workspace. So let me just show you that. So if I type in copy, oh sorry. Ooh. Sorry, this mouse is slightly reactive. Paste. Okay, so if I do that, and if I type in whos, which lists the variables that exist, it's there. But if I take off the semicolon, I now see the value, so 5, 8, all the way up to 50. Okay, so if at any point, and this is actually quite a useful thing to know, if at any point when you're doing code or trying to script something, if you have an error, it's sometimes useful just to take this but have to check that the things you think it's creating, it actually is. So what we then do is we create a random number between 0 and 1, but we have the same number of elements as we do in y, so in this case 16 elements. Okay, and then we scale them by some noise factor, which in our case is 30. Okay, so this gives us a new vector, which is our data. We'll get rid of that. So this is the original vector that went in, 5, 8, and then we've added some noise to it. Okay, oops, sorry. So we now have a noisy time series. Okay, now we want to create an X, which is our predictor. And predictor is just going to be a line. It's going to have the same number of elements as the data, Y. It's going to go 1, 2, 3, 4, all the way up to 16. Now, we want to build a model. So this, all we're doing here is building a prediction of a line. So we're going to have two things. We're going to have an intercept, two predictors, an intercept, and a slope. You know, it's called our design matrix. So we'll just turn on Y for a second. Just turn it into a column vector. This will be helpful for the statistics. So now you can see Y is that way rather. So it's now going down rather than across. And then we build a model with a set of predictors. Okay, so this is going to be our X, which is going 1 to 16, and then we've created a vector which is just a set of ones, 16 ones. And that's basically modeling the intercept from an equation of a line. So you can see here, we've got our prediction of a line, which is changing linearly. So this would be our slope. The beta parameter we get for this will be our slope. And this is a model which is just a constant. And the beta we get when we estimate the model will be our intercept in the equation of a line. Hopefully this will make more sense in a second. So we calculate the betas using this equation, which is well established. Okay, it's also a shortcut. You can use this, the pseudo inverse. So we take our design. The betas come from the equation, multiplying the data by the pseudo inverse of your predictors, and we paste. And what we get out is two values. So here, 2.911 is the beta for this column, and 21.03 is the beta for the intercept. Okay. Now if you think about that, we knew that our steps were going up in steps of 3, starting from 5, but going up in steps of 3. So you can see here we've had to scale. This is going up in steps of 1. So actually, this has worked fairly well. Not perfect, because we've added noise to the data, but you can see that it's going up in steps of approximately 3. So the model actually is fitting the data quite well. And then obviously, in this case, the intercept, we know that it started, well, our data started at 29. So when you add the intercept plus the first value, that works quite well. Okay, so the next thing now is to demonstrate that that fits the data. So we have our two betas. Our slope is 2.9, and our intercept is 21. So obviously, if we wanted to predict any new value in this grid, we could take these two values and plug them back into the equation for a line, for example, to get another point further down. Okay, and so this is it. We're going to now create our estimated response, estimated data. So we take the original predictors here, x1 and x2, and we multiply them by their betas. And hopefully this is all just the normal equation of line stuff. So this is now our predicted model. Okay. And we're now going to just plot this data. So we're going to plot our predictors against the data to begin with. So there you go. There's our line x going here, and our values of y. And we hold on. So this in MATLAB allows it to basically wait and add another plot to it. And then we add our line, our x, plotted against our estimated model. And we're going to print it in black. Oh, sorry, blue. And we hopefully will see is this is our estimated model, our best fit model here. Okay. So we had some data here, some noisy data, and we've estimated the betas. And so you can see that the intercept here would be about 21, which is what we had before. So this is our best fit model based on the parameters we've estimated using this equation here. So we've plugged them back in, taken the first beta, which is our slope, times the first predictor, which was the values going 1 to 16, and the second beta times the second predictor, which was just a constant, which was our intercept. Okay, and we'll add on label here. And there we go. So we have our observations, our data, and we have our estimated straight line, estimated fitted model. Okay. So that's basically the first step of what we're going to do this morning, today, this afternoon I should say, is we're going to basically build a set of predictors. So in our case, it was just a design matrix. It was this is our model. Okay, it's basically a constant and a predictor. Well, they're both predictors, but a constant and a slope line. Okay, that changes. A linear change. And we're estimating the betas to fit that data. So, but what we haven't done is we actually haven't tested whether that effect is significant. We haven't tested the hypothesis, we've just fitted the betas. So to do that, what we do is we basically take contrast to select the thing we're interested in. So in this case, we want to know whether the slope is significant. So our contrast is going to basically say 1 times the beta for the slope and 0 times the beta for the intercept, because we don't really care about that. That's just there to help us select the parts we want. And then we need to calculate the residuals. So we've got our data, y, and we've got our y-est. These are estimated data based on the betas we've got. Okay? And what we want to do is calculate the error, where they mismatch. So we simply just subtract them. So the residual error, is just the difference between the two. Okay? And it's this value here. 41. Now that we have that value, we can basically square it and calculate the square root. So this is just root of some squared error, which we'll use. And this is just, we're moving towards calculating a t-statistic. So these are just the parameters. And what did I call it? Sorry. Okay. This is our error. We calculate the degrees of freedom and the mean root square error. And together then we use this equation to select the contrast we want, like the condition we want, and this will give us the standard error of the fit. These MATLAB implementations are just the standard things you do. This can be done by hand for an equation line. In fact, most of you will probably have done this at some point in school where you fit a line to some data. This is just the equation line. And then we take the beta that we want. We're selecting the beta here using the contrast C. So remember, if you C is this, and beta is that. So we take C times betas, and it's just going to select this first one. Okay? And we divide that then by the standard error which we've created, and that gives us our t-statistic. Okay. And the final thing we then want to do is calculate the p-values. So basically, it should be the low tail, not the trail, but that's fine. We take the tail on the t-statistic here, and then calculate the corresponding z-score. And finally, this gives us a p-value. Tells us if this is a significant fit. Our p-value is very, very significant, unsurprisingly. Okay, so that's the key thing. So I'm just going to move up then to I suddenly realized I was working on the one in the main folder. Okay, so that's it. If you want, you can play around with this. You can change the amount of noise, for example, and see how that impacts the subsequent betas. You can also change the number of steps or the size of it, and you'll see how that will change the betas as well. So let's open code 2. And so, in essence, these are all just little examples. to give you some insight to the principles. I'm not aiming here to teach you about statistics. I'm hoping you've all got some, general understanding of statistics and what t-scores are and p-values are. Okay, so what we're going to do now is we're going to do the same basic thing, but we're going to create a bold time series. And the idea is very simple. We'll basically set a repetition time. This is the time we're sampling the data, which is once every 2 seconds. So we're going to build some data, and then we're going to build a model, and we're going to fit it, just like we did with the equation of a line. Okay? So this is the same basic principles, but instead we're going to apply them to something that looks a little bit closer to the kind of data we'll be working with. So we said our TR is 2. And we've acted as though we've collected 100 time points. We're going to collect a set of zeros. Each zero represents 1 time point. Okay, so we said 100 zeros. And I'll show you those now. Just copy. So 100 zeros. Okay, so this is like we require data for 200 seconds. Okay, 2 seconds, 1 TR for every zero. And then we mark some specific time. So we said something happened on the screen, for example, that's volume 5, volume 7, volume 20, 35, all the way through to 97. So we'll copy. So we're just specifying these times exist, and there's something happening in our experiment. You would know these times because you'd have designed your experiment. And what we then do is we take our TS, our time series, and we mark those points in time with a 1. Okay. And you can see here, now with 100 zeros, we've got a couple of 1s scattered throughout it. Okay. And what we do then is we'll plot this. Check a figure here. And this is just basically a string of zeros with a couple of 1s thrown in about. Okay. Next thing is we need to create the hemodynamic response. So this is a function in SPM called SPM href, and it just takes in information about the timing of the data being acquired. So in our case, our TR. You can do it in much more fine-grained. We take in the number of slices and that sort of thing, but for now, for this example, we'll just use TR. And we get out something that looks like this. Okay? And let's plot this. And this is the hemodynamic response we'd get if we had sampled the data. This is a predicted pattern of bold we'd see in response in a single neural response population being activated if we were sampling the data every 2 seconds. So this is our model of the hemodynamic response. If we change the TR to be 3 seconds and then create the HRF and plot it, you'll see that this is our 2-second TR, and this is our 3-second TR. So you can see you've got many fewer points on the curve, so the accuracy goes down. However, if we set the TR equals to 1 and rerun our code, so you can see there's many more points here. If we do plot, you'll see the hemodynamic response. Sorry. Is much higher resolution. So just make these slightly smaller, as you can see. Okay. So this is TR of 1, TR of 2, TR of 3. So you can see we have many more points on the curve here with the 1-second TR. So many more points of fitting the data, that sort of thing. Unsurprisingly, more data gives you more likely to have an accurate fit. But it's also that actually the model is more likely to reflect what's happening here. We've got so few sample points, there's lots of things that can go wrong, or lots of inaccuracy. Okay, so you can change that yourself in the code by changing the second line, I think. Yeah, line 3 actually, sorry. If you change the TR, you can do it there. So I'm going to set it back to TR of 2 just because our example is based on that TR equals 2. Okay. So we're now going to multiply these two together using this function called convolve. Okay? And that's going to give us our predicted pattern of bold. Now, one of the things is we have 100 time points, but when you use convolve, it smears the data out a bit further because it's kind of multiplying 100 volumes time series with something that lasts more, has a couple of time points, the SPM HOF. So you can see this is these points. So we multiply a vector of 100 zeros by this, you're going to get something a little bit longer, so we just basically truncate it, and that's all we're doing here. Taking the first 100 volumes, we'll plot it. Copy. And what you see now, hopefully, if I can figure. So this is our predicted pattern of bold. Ooh, no. Figure plot DS. So this is our predicted pattern of bold. And figure plot href. Okay. So if we took these events and convolved them with this model of the hemodynamic response we'd expect to see for any neuronal population that responded at these time points, this is the full pattern of response we'd expect to see over the whole run of the experiment, over the 200 seconds of our experiment. This is the pattern of bold we'd expect to see for any region where the neuronal populations were responding to these events. Hopefully that makes sense. So this is our predictor. This is what we're basing. It's like our slope that went from 1 to 16 in our previous code, where it's just basically saying this is what we'd expect to see for any brain region that responds to these events. So what we then can do is test the data at each point in the brain to see if it correlates with this. See if this is an accurate predictor of the response at that point. Okay, so let's move on to code 3. And we'll speed up a little bit as we go. Open code 3. And this does the same thing, but it basically produces a parametric modulator. So the responses don't always have to be set to 1. So here, we've given a different value to each response. So here, same time points, but we've given them different weightings. Saying some of these trials, the response, so let's say we want to identify any brain regions that encoded stimulus intensity, for example. We could put in additional information, so this is the stimulus intensity. The second stimulus was 3 times more intense than the first one. The third one was half as intense as the first one. So we can encode that and then test whether there's any brain regions that seem to be encoding that parameter. Now I won't copy and paste this code, it's the same as before, other than we've added this instead of having a 1 here, which is what we had before. I'm putting in a value for each thing. I'm just going to press play, and this should produce a figure for us. Okay. So there you go. That's our parametric modulator, which hopefully you can compare to the previous one. I think I've accidentally. So you can see here, instead of having all the same height, we've encoded some variation in the height, and then we've convolved that with the hemodynamic response. Open code 4. And of course, you can go through this at your own pace if you want and play around with the values. So here we're just going to build a design matrix. So again, a collection of predictors using both that information. So we're going to use the original one where the events are set to the same amplitude. And we're going to create the parametric modulator where they each have different amplitudes. Okay? And then we're going to put them together in a design matrix. 9, 7. Oh, for some reason I've left that line out. HRF equals SPM HRF TR. So if you get an error like that, you need to add that line in here, line 7. And there we go. Paste. Okay. So here's our initial predictor. I've changed color. Yeah. I'll run it one more time just to be clear. Made a slight mistake. Sorry guys, this will take 2 seconds. I'm just going to change this to x2 here. Okay, so these are basically the design matrices as they'll appear in SPM. So we have here our predicted pattern of bold response in time and our constant or intercept. Here we have the same thing, but this time with also the parametric modulator with the varying intensity. So let me just show you how that works so you can see a little more clearly. So if we take this design matrix X, and if I do figure plot X, column 1. Right, so this is the same data represented 2 different ways. So here's the initial response. So this is our pattern of bold response, but actually it's the same here. So as you go along, you can see that this is the peak. It's here at this point in time. And you can see these 2 peaks here quite close together. So it's the same data, but it's as though we're flying above here and looking down. And the brightness is how close it is to us. Okay? So this is basically a predictor, which is this, which we're going to fit to the data. And then we also have a constant, just like in the equation of a line. Okay, and the same thing goes for the other model, which you can do. You can, if you just do figure x2 and x2, we take the second column, and that's our parametric modulator. So, oh sorry, this is our parametric modulator and our response. So same onsets, exact same things are happening at the same time, same hemodynamic response function, but because we said that the neural populations in this case are encoding some parameter that we've explicitly defined, you can see the shape is quite different. What this looks like in the design matrix, which I think should be here, nope. There we go. So this is the corresponding design matrix for these 2. So, again, this is the time 1. First column is this one. And this is, as you can see here, the events, suddenly the brightest here, and then very bright towards the end as well. Okay, so this is the parametric modulator of the response at these events. So saying, okay, this is the mean response I'd expect for any brain region that encoded these stimulus, but actually there may be some residual variance, that isn't explained by this model, but is captured by this parametric modulator that says, although the neuron on average does respond, actually the population is really sensitive to this parameter here, and so when we model this, we'll get a large beta here, which will turn out to be significant. Okay, so hopefully that's clear. Again, as with all the others, the code is there, so you can hopefully tweak it and play around with it. So let's open code 5. Okay, so this is doing the same thing. We're going to build a model. We'll add some trial variations, so saying the response will vary from trial to trial. We'll add some noise. This is a more complicated model now, so this data should end up looking a little bit more like real data. And we're going to plot it, and then we're going to fit the data. And we're going to, this code is exactly the same as what we had before, but instead of using just fitting a line to some data, we're building a model. And again, here you can vary the onsets. You can vary the TR. In this case, I think I've hard-coded it to set to 2. What have I said? Yes, we have. We'll have a feeling. Probably need to move this line up here a little bit, sorry. You will see these things. Actually, it's good for you to see this. I should have fixed this in when you come to use this code, but just in case I haven't, this is so you have it. Oh no, I do actually. I take it back. The code was there, I just didn't spot it. Okay, so we should be able to just press play on this. Yes. Okay. In the end, we got some betas, and we should get a p-value, which is 0. Isn't it great? What's the z-score? Let's have a quick look. But it may be the effect is so wildly significant. The z-score thing in SPM sometimes, yeah, it tends towards infinity because there's a threshold, but the actual t-score is 14.2. So actually, it should be said there's a quirk in SPM, and you'll see this in your stats tables when you do your analysis. And here we're using the SPM framework to do the analysis. That sometimes you'll see in the z-score column this infinity listed, and it's just basically because it plateaus out. It's unfortunate, but the t-score is always there, and so the p-value's just gone to 0, which is not particularly useful. But that's fine. But in essence, there's nothing actually wrong with the code. That's it. So here we have in red our data. Okay, so this is what the code is doing, and again, you can adjust the noise level and that sort of stuff. So here's our predictive model with no adjustment to the amplitude. So assuming the data is the same amplitude in every single trial. But of course, we've added in trial variation, we've added in all sorts of stuff. Then what we do is we take our model and we've added the constant. So this is just the first, if you look at our design matrix, I think, did we create a design matrix? No, we didn't here. We've just shifted this model up to here, okay? So you can see in green here, it's the same model, but it's just been, we've added the constant, and the constant must have been somewhere about 1.1, 1.2. In fact, we can probably see what that was. Yeah, 1.1, okay, for design matrix. Let's have a quick look, actually, probably just reduce that figure without too much hassle. Yeah. Figure. Just to show you the model. So that's the predictor. I'm not turning, and of course we can turn it to grayscale, but I'm not going to bother. Okay. And then we've taken the initial fit and we've multiplied it by the predictor. Okay, which is the other beta. So it's if we take the first beta here, it's this value. So we've multiplied the value. So we've added this value, and then we've multiplied it by the first column by the. So we multiplied the second column by this, and multiplied the first column by this, and added them together. So if you remember that equation here, the fits are given by this one here. So the first beta multiplied by the first predictor, plus the second beta multiplied by the second predictor. So 2.71. So in essence, what we've done is we've added the constant 1.1 up here, and then we scaled it by 2.71. And you can see it fits the data quite well. So again, in this code, you can tweak the amount of noise, you can do other things, you can tweak the amount of trial variation. So in this case, but again, you can see here that the constant was only 0.5, so the original intercept, the intercept was set to 0.05, but with the noise, with other things, it kind of changes. Also, we've added a random variation here. You could manually select that if you put in something if you wanted. And like using the previous code 4, you could build in an extra predictor, which is the parametric modulator, and then you change this to include betas. So let's open code 6, and we'll. Oh, and this is showing the impact of using basis sets, which I'll play, but I don't think I'll focus on right now. I think that's probably too much. So one of the things is we can use more than one basis set to fit the data. So the standard canonical HRF is okay, but we know from subject to subject the response varies. So let's say we have some events here. This is a standard canonical model of the HRF. Okay. But the problem is the hemodynamic response varies from subject to subject, from time to time. It's affected by drugs, these sorts of things. So often just using the canonical HRF, which is here in blue, isn't a great idea. But what we can do is include a model which is the temporal and dispersion derivatives. Let me see if I've got that in my slides. We've done convolution. Oh, sorry, gone the wrong way. This is explaining parametric modulation, so we take the initial response and scale it. I wanted to talk about image response functions. I thought I had them here. Sorry, take 1 second. Here we go. So yeah, so basically captured this variation in the shape with the canonical HRF here, but we have this temporal derivative. So it's just the derivative of this function with respect to time. But you can see it has an earlier peak and then this undershoot that happens quicker than this. And what this does, if we get an extra regressor in our model that is basically the same onsets we had but involve the temporal derivative. And the key feature of the temporal derivative is if the response, let's say, is slightly earlier than it's predicted by the canonical, it'll be caught by this beta, this part of the curve. Okay, the temporal derivative response. And so we'll have a positive beta on this temporal derivative. If, however, the response is slightly delayed compared to what the canonical HRF says it should be, you'll get a better fit to this part of the data, but that'll be a negative beta. So the betas for the temporal derivative model reflect the timing with respect to the canonical. Okay, so what you'll get is you'll get a beta for the canonical and a beta for the temporal derivative. And so a positive beta for the temporal derivative means the peak is reached slightly earlier, but a negative one means it's reached slightly later. There's also the dispersion derivative, which is to do with whether this width here, the dispersion of the canonical HRF, varies. So maybe the response is normal in the time it reaches peak, but it's much wider, it doesn't come back down to here. So the dispersion derivative captures that. So if the response is much wider, it'll fit the data here, and we'll have a negative beta. If it's much narrower, it'll fit the positive derivative here. And the weighted combination of these three basis sets, is what the term is used, can give a much more flexible fit to the data. Okay, so it allows for variation in the temporal peak, the peak latency, the temporal response, and the overall response width. And that's what this example of the code is doing. So there we go, that's a temporal derivative. We take our initial model. So this is what it would look like. It's 3 columns, one in green, one in red, and one in blue. And how does that look in the... I'm going to close these so they don't get in the way. So here we go. Our initial response for the canonical HRF, the temporal derivative, the dispersion derivative. So it's the same onsets, but they're involved with different basis sets, and then these 3 basis sets. And then we have our intercept. And what you see is the data here with the fit-in model, and it fits quite well. Give me that. And again, the fitted data. This is the original one from earlier on. Okay. So the key thing with the code really is just to have a play around with it. You can change parameters and see how they go. So this here is HRF is dispersion derivative, and you'll see we'll actually be entering in this information later on within SPM. And this just gives you some information about the shape of the HRF. So here we can manually specify the HRF to be a different shape or whatever you want. So that basically gives us 2 different HRFs. So what I've done actually in this case is I varied the HRF when I made the data to begin with. So in this case I changed this parameter slightly, and I used that then to create this kind of synthetic data that we then subsequently build a model to try and predict. Okay. So then here we create, this is where we're building our design matrix, our predictive model, and we're involved with multiple basis sets, which is happening here. Okay, this gives our model with 3 columns, or well, 4 columns if you include the intercept, and then we fit that to the data. So I've manually first altered the hemodynamic response. So I'm kind of synthesizing data as though this person, for example, was on a drug or something like that might have changed the hemodynamic response. Okay, and I think I'll leave it there. There's another piece of code that does, if we do ls. So these 2, well, actually, let's just run them quickly. Let's run the stats talk. Okay, this is code I've slightly modified. and then we'll return to random talk later on. Box code 1. CD EG scans. Actually, before we do that, we add path just so it remembers the scripts. Change directory to go up one level, and CD EG. Oh no, sorry, I'm wrong. CD EG scans. And we'll stats talk. We say this current location. It must append. There we go. And this is basically just building a design matrix, building a two-sample t-test. So this is just code from Cambridge that basically explains some of the basic principles. So again, task difficulty can be code in the model. Actually, yeah, I'm not going to worry about that too much. Okay, let's stop there and we'll come back to